spanning trees from the graph, as well as we talked about some algorithms for finding out the minimum spanning tree, right? And how many algorithms we can use in minimum spanning tree? There are two algorithms. One is Kruskal's algorithm and another is Prim's algorithm, right? And what is the main principle of Kruskal's algorithm, or what is the principle of Prim's algorithm? Their motives are same, right? Why you use those algorithm? For finding out the minimum spanning tree, right? So in Kruskal's algorithm, what is the working procedure of Kruskal algorithm? When the graph is given, so we can take one node as a source node. Do we need to take any node as a source node in Kruskal algorithm? What is the working procedure of Kruskal algorithm? What is the first step? In which algorithm we need to take a source node or source vertex, in Kruskal's algorithm or in Prim's algorithm? In which one? You already forgot that algorithms, Kruskal's and Prim's algorithm. Hello, I'm asking something, right? Hello? Can you hear me? Hello?
Yes, ma'am. We can hear you.
Yes, I'm asking that in which algorithm we need to take a source node. In Kruskal's algorithm or in Prim's algorithm?
Source.
I can believe that you already forgot those two algorithms. Just discussed those two algorithms previously in the last class. How many of you have actually forgotten those two algorithms? Hello? If you have problems in previous topics, then how I can start a new one? Hello, can you all hear me?
Yes, ma'am.
Yes, I'm asking, if you have problem in Kruskal's or Prim's algorithm, do I need to discuss those topics again?
Ma'am, kindly repeat it again, then it will be better.
Which one?
Kruskal algorithm.
Kruskal algorithm. Okay, so what is a graph? We all know what is graph, right? But do we know that when a graph will be given, can we identify that graph? That which graph, what type of graph is given? I think we all can identify the graphs because we know what are the characteristics of different types of graphs, right? So we can take a graph with 6 nodes. So these are the nodes A, B, C, D, E, and the last one is F. So how many nodes are here? 6 nodes or 6 vertex. So can we call it graph now? No, because a graph consists of some vertices as well as some edges. And what is edge? The connecting line of 2 nodes. So when we are connecting these 2 vertices A and B by this connecting line, now we can call it an edge. Right, we can take another connecting line between B and D, and between D and F also. Suppose E and F are also connected, C and E are connected. Suppose we didn't draw any line between A and C. So is this a graph? Yes, it's a graph, but this graph is disconnected. And if we want to draw some spanning trees from this graph, the first thing is the graph cannot be a disconnected graph. We need to take a connected graph. So now this is a connected graph. Is it strongly connected graph? No, it's not strongly connected graph because we didn't, or all these vertices are not connected with all the other vertices. That's why it's not strongly connected graph. But still, we can add some other vertices, B to C, suppose C to D. Okay, so this is a connected graph, right? So this graph G consists of a set of vertex and a set of edges, that is V and G. Now, how to create these spanning trees? Spanning tree is one kind of graph, or this is a subgraph. right? So this is subgraph. That means that graph, that spanning tree should contain all these vertices A, B, C, D, E, F. In that spanning tree, if you want, you can change the position of these nodes, but you cannot take, I mean, more than 6 nodes in your spanning tree or in that subgraph, but their positions can be changed. Okay. So now in that subgraph, the number of vertices will be same, but what about the edges? The number of edges,
N minus 1.
I mean, in that spanning tree, the edges will be a subset of the edge of this graph. The edge is subset of this graph. Okay, that means in that spanning tree, the number of edges will be less than here, less than the graph, right? So how many edges we can draw in that spanning tree? V minus 1 number of edges. So in that new graph, in that spanning tree, the number of vertices will be 6 and the number of edges will be 5, because here the number of vertices equals to 6. Okay, so this is, suppose initially the spanning tree is empty because we didn't include any nodes here, or we didn't draw any lines here between the nodes. Okay, what is the first step? How to take the spanning tree? If this graph is a connected graph, then we can draw several spanning trees from this graph. Okay, if the graph is connected, we can have more than one spanning tree, right? We can just take any of, how many edges are here? 1, 2, 3, 4, 5,
8.
6, 7, 8. There are 8 edges, so we can take how many edges from those 8 edges? 5 edges, only 5 edges, right? So after taking those edges, after taking 5 edges, we can create a spanning tree. But how we can find out that is this the minimum spanning tree? So at that time, we need to have some widths, right? That means we should assign some widths, some values to these edges. So suppose the value of this edge is 12, for this edge it's 7, it's 4, it's suppose 3, 1, 9, 15, and it's 3. So now this is a weighted graph. Okay. So here, if we want to find out, if we want to create some spanning trees, the first step is remove all the loops and all the parallel edges, but we didn't take any loops or parallel edges here in this graph. Okay. What is the next step? By taking only 5 edges, we can create the spanning tree, but one thing is we cannot take the edges where the edges will create a cycle. What is cycle? This is the path where the starting point and the end point will be same. So we can't take any, we can't add any cycle in that spanning tree. In this way, we have to add the edges, right? So now there are 2 algorithms for creating a minimum spanning tree. The first one is Kruskal's algorithm and another is Prim's algorithm. Okay. So in Kruskal algorithm, the first step is after removing all the parallel edges or all the loops, the first step is now to organize, to store the edges according to their widths, right? So we can store the edges in ascending order. So here, which edges has the minimum value? This one, CD. That first you store that edge, CD. So here we can write all the edges along with their widths. So CD and its weight is 1. And then the next one will be BC or EF. So the next one is BC with weight 3. And for EF, the weights are same, 3. And which one will be the next? AC. For AC, the weight is 4. And the next one will be BD, and its weight is 7. After that, CE with weight. What is the weight of this CE? 9. And the next one will be AB, and its weight is 12. After that, DF. 15. So how many edges we have stored? 8 edges. But in minimum spanning tree, the number of edges will be 5. So we can take 5 edges from those 8 edges, but we cannot just randomly choose any edge from here. We have to start from the first edge. We can add the first one. So here, the first edge is CD. That means which 2 vertex we need here? The vertices C and D. Okay, so we can use the same representation. We can create the same structure like this graph, or if you want, you can change the position of these vertices. It's up to you. So suppose we want to create the same one, same structure. So this is C, and then the next node will be here, D. And between these two vertices, the edge is CD and its weight is 1. So this is our first edge in this minimum spanning tree. Okay, now the next one is BC. Where is B? So we need one vertex now B, and here we are assigning another edge from B to C, and that edge weight is 3. Okay, and now the next one is EF. Where is E? This one. So can we take that HEF? Can we add an edge between these two vertex E and F? Yes, we can take an edge between E and F because it's not creating any cycles here. So its weight is 3. Okay. Now the next one is A and C. This is A. So can we take that edge AC?
Yes, ma'am.
Yes, we can take that edge. So AC and its weight is 4. And now already we have added 4 edges. So we can take only one edge. Okay. So now the next edge is BD. Where is B? This is B. And if we take an edge here at that time, it will create a cycle. That means we cannot assign any edge between these two nodes B and D. So we'll ignore that one. Why we didn't take that edge? Because it after adding that edge, it will create a cycle. That cycle will be BDCB or CDBC, or it can be DBCD. Now the next edge is CE. Where is C? This is C. So can we take that line? Can we take that edge?
Yes, ma'am.
Yes, it's possible. So CE 9. How many edges are here? 5 edges. So now we can test the next edges also. Suppose take the next one, AB. If we take this one, it will create a cycle. That means we can take only how many edges? Only n minus 1 edges. So this is our minimum spanning tree. Okay, so we after adding all these weights, what will be the value of all the edges? 4 plus 3, 7, 7 plus 1, 8, 8 plus 9, 17, 17 plus 3, 20. So 20 is the weight of the total spanning tree. And this is the minimum spanning tree. And which algorithm we applied here? The Kruskal's algorithm. This is the Kruskal's algorithm. Clear? Is it clear?
Yes, ma'am.
Okay. And this is a minimum spanning tree. And we know that one characteristic of a tree graph is all the paths will be a simple, unique, simple path. That means between any two nodes, we can find only one path, right? So look at this. Suppose here, if A is our starting point and if D is the starting point, there will be only one path between A and D, and that path is A, C, and D. What about between B and EF? Between B and F, the path will be a unique, simple path. So here the path sequence is B, C, E, and F. You cannot find more than one path between any two nodes. That's why this is a tree graph, or you can call it spanning tree. So this is Kruskal algorithm. Okay, and another one was Prim's algorithm. What is the difference between Kruskal and Prim? This one, in Prim's algorithm, we don't need to store the edges, right? We can just take one node as the source node, and then we have to find out the adjacent nodes of that vertex of that node. Then we can move forward. That is Prim's algorithm. Do I need to discuss that one also?
No, ma'am.
No, ma'am.
Okay. So this is Kruskal's algorithm, and where we can apply it in a connected graph. And if we want to find out the minimum spanning tree, then we can apply Kruskal's algorithm or Prim's algorithm. Okay. So now our today's topic will be about shortest path algorithm. What is paths? If a source is given and the destination node is given, then if between these two paths, if there is a way for traveling from that source node to the destination this is T. That is destination node, that's called the path sequence, right? And in path sequence, we have to include all those vertices, right? So what is shortest path algorithm? Now, after taking a graph, that graph can be a multi-graph, it can be connected graph, or it can be strongly connected graph. And between any two nodes, we can find more than one path, more than one way. So which one will be the shortest one. How you can find it out? By calculating its weight. But sometimes when a largest graph is given, when the number of vertices may be 10, 20, 30, 40, so each of those vertex can have its own value. So let me take a graph first. Suppose this is a graph with um, 8 nodes. The first one is 0 or right, A, then B, then C, D, and this is E, F, Q, and the last one is H. So how many vertices are here? 8 vertices, right? Now we can add some lines here between A and B, A and E, BE, and another edge is BC. Then okay, here we can take one more vertex, that is I. So CI, then FI, one is EI, F, CG. Is this a connected graph?
No, ma'am.
EFG.
ENG. Okay. So now this is a connected graph. And how many vertices are here? 9 vertices. A, B, C, D, E, F, G, H, and I. So there are 9 vertices. And how many edges are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right?
Yes, ma'am. 14.
There are 14 edges. So number of vertices are 9 and there are 14 edges. Okay. So here, if this graph is connected graph, that means from one node we can easily travel to another node. Okay, so our source node can be A and the destination node can be D. Okay, so in how many ways we can travel from A to D? One way is A, B, C, D, and another is A, E, I, C, D, and another can be A, E, F, I, C, D, or another can be A, E, F, G, then D. So there are several paths for traveling from one point to another one, right? So how we find out which one will be the shortest path? If we assign some values, if we assign some weights, then we can find out the shortest path. But another thing, it's really time consuming that every time we are taking some path and then we are counting the weights, right? It will take so much time. That's why we now apply one algorithm which will provide us the shortest path between any two nodes. And here we'll apply Dijkstra's algorithm. So this algorithm is used for calculating the shortest path, right? But this Dijkstra's algorithm is called single source shortest path algorithm. That means here, if you are applying the Dijkstra's algorithm, then we can take only one node as the source node, right? And that node can be B, C, D, I, E, F. We can take any node as the source node, but the number of source node cannot be more than one. That's why it's called single source shortest path algorithm. Okay, so the source node can be A, it can be B, anyone. Suppose we are taking this one. This is our source node. So now in this algorithm, now we can find all the possible path or all the shortest path between A and any other vertices, between A and B, between A and C, A and D, A and E. That means we can find out the possible path with A and how many other vertices? 8 other vertices. It is B, C, D, E, F, G, H, I. Okay, so at the starting of this algorithm, Dijkstra's algorithm, the first step is, if it is our source node, look at this, did we assign any loop here? No. If there is a loop, then we can add some weights here, but we didn't take any loops. At first we can add the weights. Suppose the weight of this edge is 4, this is 8, 7, 9, 10, 14, 4, 2, 6, 1, 7, it's 2, and This is also 8. Okay. And here 11. So this is now a weighted graph. Okay. So the first step is, if this is our source node, then its distance will be 0. At first, we have to assign some distance to each of these vertices. And A is our source node. That's why its distance will be 0 because we didn't assign any loop here. Right, so here we have to assign some distance to each of these vertices. For the source node, the distance will be 0, and for the other nodes, the distance will be infinite. That is, we don't know what is the distance between A and B. That's why we are assigning infinity here. For all these vertices, the distance will be infinity. That is the first step of Dijkstra's algorithm. So we are assigning the distance of each of these vertices as infinite. Clear? What is the first step?
Yes, ma'am.
Okay. Now after that, if A is the source node, now look at this graph. Which two nodes are the adjacent node of A?
B and
There are
E.
only two nodes, B and E. So at first, we will find out the shortest path between A and B and A and E. So which one will be taken first?
A
So
and B.
there is a formula. Okay, so we can take the shortest one here. The shortest weight is 4, so obviously we'll take 1. But here we can consider these weights as the cost between A and B. But the main distance depends on this value. Initially the value is infinite. So here the value of B and E are same, that is infinite. So we can just take in one. Suppose we're taking B first. Okay, so what is the distance of this vertex B? Initially it's infinite. Now we are going to calculate its actual distance from A. So how we can do it? What is the distance of A? The distance of A, this is a formula, I'm writing it here. So suppose we are finding out the distance between this node A and this node B. So we can assign a value E and V here. Okay, suppose the starting node is U and the end node is V. So the equation will be D of U plus cost of, that is C, U and V. Okay, so what is the distance of U now? The distance of U is 0, right? So 0 plus, what is the cost of U and V? The cost is 4. So 0 plus 4. And the equation is D of U plus C of U and V if it is less than the distance of V. And here B equals to, this is V, this is our destination node. So 0 plus 4, is it less than infinite or greater than infinite? 0 plus 4, that is 4, is less than infinite, isn't it? So if this condition is true, if D of U plus C of U and V less than D of V, then we can change the distance of V. Then the distance of V will be D of U plus C of U plus V. This is the rule of Dijkstra's algorithm. The first step was we have to find out which one is a source node. So A is a source node and its distance will be 0, right? And here to all the other vertices we have assigned the distance as infinite, right? Now the next step is, if A is a source node, then find out which vertices are its adjacent vertex. So B and E are its adjacent vertex, so we can just take any one from these two vertex. Suppose B is now the destination vertex, right? So now we have to find out, we have to apply these rules here. What is the rule? D of U plus, that is distance of U plus cost of U and V. Is it less than the distance of V? Yes, it's true. So if it's true, then you can change the distance of this destination node. How you can change it? The equation will be D of V, that is distance of V equals to D of U plus C of U and V. So here distance of U is 0 and the cost of U and V is 4. So now the new value, the distance of B will be 4. Is it clear how we are changing the distance?
Yes, ma'am.
We are just using this equation, this rule. If the distance of U and the cost of U and V is less than the distance of V, then change the distance of V. How we can change it? Just assign that value, distance of U plus cost of U and V. So now this is the new distance of V. Okay, what is the next step now? There is another adjacent vertex of A, that is E. So now you're going to apply the same rule here. What is the distance of A? The distance of A is 0, right? And the cost between A and now here E is V. So this is our destination vertex. Okay. So 0 plus 8 equals to 8. Is it less than infinite? Yes, it's less than infinity. So the new distance of E will be 8. Clear? Is it clear?
Yes, ma'am.
Okay. So now there are two nodes, B and E. Just like the previous one, we have to find out which vertices are the adjacent vertex of B and E, but we can't take both of them at the same time. We have to one, which node will be taken first, B or E. Now it depends on the distance of that vertices. So here, B, the distance is 4, and for E, the distance is 8. So here, the distance of B is less than the distance of 8. So we'll take B. So already we have visited this node A. Okay, now the next node will be B. Okay, so here which vertices are adjacent vertex of B? There are 3 vertex A, but this is already visited, so we will not consider this vertex again. And one vertex is C and another is E. So there are 2 unvisited vertex from B. One is C and another is E. So now we are going to apply the same rule here. This is the rule. So what is here now? U equals to B. This is our U. And which one is V? This is our destination vertex. So C is the destination vertex. What is the next step? Apply the rule here. That is D of U plus C of U and V. What is the distance of U? Here equals to B. And the distance of B is 4. What is the cost between U and V? That is between B and C. The cost is 8. So 4 plus 8 equals to 12. Is it less than infinity? Yes, 12 is less than infinity. Now change the distance of V. That is, change the distance of C. The new distance of C will be 12. Why change that value? Just look at this rule. The rule is if D of U plus C of U and V is less than D of V, then change the distance of V. Okay, so now the new distance of C is 12. Okay. Another unvisited vertex of B is E. And what is the distance of B? 4. So 4, and it's the cost between B and E is 11. So 4 plus 11 equals to 15. Now U, that is B. And what about V? V is E, right? How you can apply the rule here? So D of U, that is D of B, equals to 4. What is the cost between U and V? 11. So now 4 plus 11 equals to 15. Is it less than the distance of E? Now the distance of E is 8, not infinite. We already changed it one time. So the distance is 8. Is it true? No, this condition is now not true. When the condition is not true, we will not change the distance of this destination node E. So its value will not be changed. Clear? Because it's not less than 8. Okay, so now here how many nodes are visited now? A is a visited node and also B. Okay, so now the next one is C or the next one is E. Which one you should take, C or E?
C.
It depends on its distance. The distance of 8, the distance of E is less than C, so we'll take this one, not C. Look at this. Here we have 2 vertices, one is E and another is C. Now compare between their widths. Which node has the minimum weight? That node E. Its distance is 8, so we'll take this one. Now this node E has how many adjacent vertices? 4 adjacent vertices. One is A and B, I and F. But these 2 vertices are already visited, so we'll not take these 2 nodes or 2 vertices. Now from E we'll consider this vertex I and another one is F. Okay, so we'll apply the same rule here. So now this one is our source, this is U, and this I is V. Apply the same rule. D of u plus C of u and v. Here the distance of u is 8. 8 plus 7 equals to 15. And what about the distance of this destination node I? The distance is infinite. So 8 plus 7, 15 is less than infinity, so we can change its distance. Now the new value of I is 15. This is the new distance of I. Okay. Now this E has another adjacent vertex, that is F. Okay, so now the distance of E is 8 and the cost is 1. 8 plus 1 equals to 9, and 9 is less than infinity, so we'll change that value. So here the distance of F is 9. So now we have already find out the distance for all the adjacent vertices of E. So E is now visited. Okay, so now we have three vertices C, I and F. So which one will be the next node? It depends on its weight or distance. The distance
You
of
will
C
be
is
the next node.
the distance of I is
Sorry,
15.
F.
Yes, F. Now we can take F because its distance is 9, which is less than the distance of C and I. So the next one is F. So which nodes are the adjacent nodes of F? One is E and one is I and another is G. But this E is already visited, so we'll take only these two vertices I and G. So when U equals to F, this is our source node now. What is the distance of F? Distance is 9 and the cost matrix, the cost is 6. So 9 plus 6 equals to 15 and is equals to the distance of I. When the value is equal, at that time we don't need to change its value. Okay, so we'll not change the distance of I because their values are same. Okay, now the next one is G. The distance of F is 9 and the cost is 2. 9 plus 2 equals to 11 and it's less than 11. So now this vertex is also visited. Right? Okay. So now we have these three nodes C, I and G. So which one has the minimum weight now? This vertex G. This has the minimum distance. Okay. And G has how many adjacent vertices? 4 adjacent vertices F, C, D and H, but this F is already visited, so it has 3 unvisited vertices, that is C, D and H. So now we'll apply this rule here. So now G is the source node, so its distance is 11, and between G and C, what is the cost value? Cost is 4. So 11 plus 4 equals to 15. Is it less than the distance of C? No. So we will not change this value 12. Okay. Now the next node is D. What is the distance of G? 11 and the cost is 14. 11 plus 14 equals to 25. Is it less than infinity? Yes. So change its distance. The new distance of D is 25. Okay. One more vertex is here, H. The distance of the source node, that is G, is 11 and the cost is 10. 11 plus 10 equals to 21 and it's less than infinity. So change the distance of H. The new distance is 21. So now this vertex is visited. So which one is the next node now? This C and I. Now compare these two vertex. Which one have the minimum distance?
C.
C. Okay. So now the next vertex is C. Which vertices are the adjacent vertex of C? One is B, but it's already visited. Another is I, then G and D. So B and G are visited. We can take only two vertices, I and D. So here C is our source vertex, source node, and its distance is 12. So 12 plus 2 equals to 14. Is it less than 15? No. So it's less than 15. 12 plus 2 is 14. So again, we will change its value. Now the new distance of I is 14. Okay. One more adjacent vertex of C is D. So the distance of C is 12. 12 plus 7 equals to 19. Is it less than 25? Yes. So again, change its distance value. So now the new distance of D is 19. So C is now visited. Okay. So which one will be the next source node?
I.
This I or D? Yes, I. Okay. So this I has how many adjacent vertices? 3 adjacent vertices, that is C, then E and F, but all the vertices are already visited. That means this I is now visited. We don't need to apply this rule here because all the adjacent vertices of I are visited. That's why now this node is also visited. Which one is next now, D or H? Obviously D. The distance of D is 90. So this is the source node and there are 4 or 3 adjacent vertices of D. 3 adjacent vertices C, G and H, but both of these vertices G and C are visited. So now apply this rule here between D and H. The distance of D is 19 and the cost is 9. 19 plus 9 equals to 28. Is it less than 21? No. So we will not change the distance of H. So now this node D is visited. Okay. After that, this is the one node H, and do we need to calculate or do we need to apply these rules here? No, because all the other vertices are visited, which means that the adjacent vertices of H are already visited. Look at this. Look at the graph. The adjacent vertices of H are D and G. They are already visited. So this 21 is the distance of H. Okay, so now all these vertices are visited and we got the distance for each of these vertices, right? In this algorithm, we took this node A as our source node. So this is the source node, and now for the other vertices B, C, D, we got the value. For B, the distance is 4. For C, the distance is 7. For D, the distance is 19. For H, it's 21. For G, 11. For F, 9. For E, 8. Okay, so after applying or after visiting all the vertices, now we got the shortest path. Why we applied this Digital-Castros algorithm? For finding out the shortest path between A and any other vertex of this graph. So now the shortest path between A and B is 4. The distance is 4. So what will be the shortest path between A and C? Which one is the shortest path? The shortest distance between A and C is 12. And which one is the shortest path? This one, A, B, and C. There are so many paths between A and C. One is A, B, C. Another is A, E, B, C. And one more is A, B, E, A, E, F, I, C. But which one is the shortest path? From this distance, now you'll get to know that which path sequence is the shortest path sequence. The distance is 12, which means that this is the shortest path between A and C. Here the weights are 4 and 8. So 4 plus 8 equals to 12. Which one is the shortest path between A and D? The distance is 19. So which one should follow for getting the value 19? Can we find it out?
A, B, C, D.
A, B, C, D. 4 plus 8, 12. 12 plus 7 is 19. Very good. So this is the shortest path between A and D. And now the next one is between A and G. The shortest distance is 11. So which one is the shortest path?
A, E, F, G.
A, E. Which one?
A, E, F, G.
Very good. A, E, F, G. So this is the shortest path between A and G. So this is Digital-Castros algorithm where you can easily find out the shortest path sequence between the source node. Here the source node can be only one. Okay, and any other vertex of this graph. So is it clear? Digital-Castros algorithm?
Yes.
So I'm explaining the whole process again. Digital-Castros algorithm is called single source shortest path algorithm, which means that in this given graph we can have only one source node. Then you can find out the shortest path between that source node and any other nodes of or all the other nodes of this graph. Right, so here you just have to apply this rule at first, assign some weights, assign some distance to each of these vertices, and that distance will be infinite. Then you just have to compare the value of D of and V with the shortest distance as well as the shortest path. Clear?
Yes, ma'am.
So in the next class, we'll apply the same algorithm, Digital-Castros algorithm, but on a directed graph. This graph is undirected, so we can take any edge in any direction, that is from A to B or B to A. But in the next class, we'll take a directed graph and then we will apply the Digital-Castros algorithm.
Ma'am, isn't our class still this week?
Actually, I don't know about it. Okay, so it's not confirmed yet. So maybe I can let you know in the next week.
No, we heard that our on second of next month, all assignment will be shared.
Actually, I haven't heard anything about it.
All right, ma'am. Got it.
But in the next week, I'll give you an assignment, maybe on 2nd May. Okay.
Okay, ma'am.
And in that assignment, the topics will be included from all the chapters, that is from chapter 1 to chapter 9. So far, how many chapters we discussed? 9 chapter from 1 to 9, but okay, we'll discuss these things in the next class about the, syllabus of this course. Okay. Now please response 1.